Hello, welcome back. Welcome to discussion 10 for CS61B. Today we're going to be talking about depth first search, breadth first search, and shortest paths. First things first, just some announcements out of the way. Midterm 2 is this Wednesday. Might already be past at this point when we post the video. Homework 3 was due on Monday, and there is no lab this week once again. So if you need help during that time, you can go to office hours instead. Some content review. So the first thing we're going to talk about is just graphs, like we talked about trees last week. So graphs are just structures that contain nodes and edges. And so this would be a node, and this would be an edge. And edges/graphs can be directed or undirected. And a directed graph has little arrows at the end of its edges, and it says there is a path from A to B, but there isn't necessarily a path from B to A. It's a one-way street. An undirected graph doesn't have this constraint. If there is an edge between any two nodes, there is a path from A to B and from B to A. Graph representation. So graphs are pretty cool and all, and we know, and like trees though, we need to have a way of representing them in code so we can actually, do stuff. It might seem a little daunting at first, but there's two main ways that we represent graphs using data structures. The first way is called an adjacency list, and the way it works is that you kind of have a data structure that has all of the nodes on this side, and then on this side it has all the nodes that it has a direct connection to. So in this case, A directly has a path to B and C, and so both of those are here. You can think of this as kind of resembling a hash set of sorts. And then you have B, and it has a direct path to only E. C has a direct path to only F. D has a direct path to only B, and F has a direct path to only D. And E has no direct paths to anything. This identity lists are useful, but they can be a little bit more time consuming than our next method because, for instance, what if A had a direct path to every node in this list, right? You want to check, hey, does A have an edge to E? Then you would probably have to go through every single item in this. And so that might take theta O of n time. And so a way to make that operation faster is to instead use an adjacency matrix. An adjacency matrix is like a 2D array where we have all of the nodes repeated on this side and on that side. And so having a value be 0 means there is not an edge from that node to that node. So for instance, there is no edge from A to D. But having a 1 means you have an edge from A to B. And you can have 1 if the graph is unweighted or if all the edges have the same weight. And if you have a graph that has weights to its edges, this takes 8, but this is 7, so this path would be considered longer than this path, then you can replace these ones with the actual edge weight. And as you know, indexing into matrices is very fast. And so because we know exactly what we're looking for if we're trying to find something, all we have to do is immediately index in. Now, there is obviously going to be a downside. If you're going to do a depth first search, very similar to how we did, or a breadth first search, either one, very similarly to how we did it for trees, you have to search through the entire adjacency matrix every single time. You have to search through the entire row every single time when you're searching for what children it may have. Because here, all you have to do is be okay, B, C, put them on the queue, we're good to go. But for the adjacency matrix, we don't necessarily know when we're done looking for children. So we have to traverse all n possible children every single time. So yeah, pros and cons to both. The pros and cons aren't the most important, but it's just nice to be aware of them. We won't really ask you to do too much with code and graphs, but this is one of those things where it's helpful to know how you would be able to implement these things if you had to. So graph searches. So thinking back to when we talked about tree searches, these are very similar. And so breadth first search is very similar to how we talked about it in trees, except of course now we have possible loops. And so the way we say that is we can't visit a node that we've already seen. And so if I started A for breadth first search, I use a queue. So I add A to the queue and then I pop it, and then I add B and C to the queue because I go like that, and then I pop the higher one, so I pop B, and then I add E to the queue, and then I pop C, visited B, we're going to visit C, and now we're going to add F to the queue, and we're going to pop E out, and E has no children, so there's nothing to add, and now we're going to pop F, and we're going to add its child D, and then we're going to just pop D, and then we hit a node that we've already seen, so we're done with this path. There's nothing left on this queue, so we are done with our breadth first traversal. Depth first search is very similar to the one we did in a tree. There are pre, post, in order traversals. There are pre and post traversals of graphs. There actually aren't in order traversals because what even is a left child on a graph? So the way to think of depth first search is it uses a stack. And so an example on this graph, again, would be, so you have A, you pop A, and now you have B and C added, and we're going to add them in reverse order. Maybe I should move this to the bottom of my stack. Hold up. That might be more visually reasonable. Okay, and now we're going to pop the item on the top, so we're going to pop B, and we're going to add its kids, so we're going to add E. We visited these nodes. And we've obviously we're going to visit E now, and E has no children, so we're going to go move to the next item in the stack, and we're going to pop C, and we're going to add F. And so as you can see, the difference is where it's more of a last in, first out system, and so the last item you add to our stack is the next item we're going to visit, which results in you kind of moving in all the way down, and then coming back up, and then all the way down, and then coming back up. Versus breadth first search just kind of sweeps based off of how far away the node is from the root. Now we're going to talk about something that's a little more complicated, and it's a hard topic, I will admit. So if you're struggling with this, there's lots of practice problems that we have in various places, and I urge you to do them because it's a little more complicated than things we've been doing in this class in the past, in that it's not hard in that it's a difficult thing to do. It's just hard in that there's a lot of different things that you have to do in a specific order, and it's easy to forget what you have to do. So this is called Dijkstra's algorithm. And the point of Dijkstra's algorithm is to find a shortest path from one node to every single other node in the graph. And so the way that works is you start here. So A is going to be our root node. And now we are going to try to figure out the shortest path from A to every single other node. And the way we do that is we use a priority queue. So let's say we have our priority queue here. And so we have A with distance 0 from A. So we're going to pop that first. And now we're going to add B with distance 7 and C with distance 1. And of course it's a priority queue, so we can sort by how far away. So we're going to add C like that, and B like this. And now we're going to pop C. And once we've popped something, it's set. This is the distance. This is the final distance to that item. So the final distance that we determined from A to A is 0. The final distance we've determined for A to C is 1. That's that. But until we pop something, we can still edit its distance. And so next thing we're going to add is F. And F has a shorter distance than B. So we're going to actually pop it. We're going to add it to the queue, and it's going to end up higher up. which I hope seems reasonable based off of the fact that we've implemented a priority queue already. So now we just pop F, add D. Oh, sorry, I messed up. F is actually going to be 3, I wrote 2. The reason, of course, that it's 3 is because the distance from A to F is a distance from A to C plus a distance from C to F. Same thing applies, I just messed up the math. And now we have D that we're going to add, and this time the distance from A to D is going to be 4, which is still less than 7. So now we're going to pop this, A, B, C, D, E, F. And so F is set at 3, D is set at 4. And now we have an interesting situation where the next node we visit is B. And if we were doing traditional depth first, breadth first, any sort of search, we would stop and be like, oh, B is already in our queue, we don't have to do anything. But we actually haven't visited B yet, right? Well, I don't know what just happened. We haven't actually popped it from the queue. And so now we can actually re-add B with a better priority, because this is only 5 versus 7, which is obviously a shorter path. And so now when we visit B, we can say, oh, the shortest path from A to B is 5. It takes us all the way around, but it is 5 ultimately. And the last thing we do is we add E, which is E7, and then we visit E and pop it, and we add it to our list. And so that is the shortest distances from A to each of these nodes. And so if you want the actual set of steps, I felt like doing an example would be easier, but the set of steps is you pop a node from the top of the queue, you add and update the distances of all the children of the certain node. So if the child doesn't already exist in the queue, then we're going to add it, and if it does, we're just going to update its priority. And then you're going to resort the priority queue, and we're going to finalize the distance for the current node to the root. I guess that part can happen at any step on this process. And then we repeat, and we keep repeating until our priority queue is empty. The next algorithm is called A star. And A star is very similar to Dijkstra's. There's two big differences. First of all, the point of A star is not to find the shortest path from one node to every other node. The point is to find the shortest path from one specific place to a different specific place. So if we're talking about like a US map, right? I don't want to find the fastest way to get from San Francisco to every single city in the US. I only need to find the fastest way to get from San Francisco to New York. And so this is a faster algorithm, and it operates very similarly to Dijkstra's, except for the fact that we use a given heuristic, so you guys don't have to figure out how to come up with that heuristic. That's a 188 problem. But we will give you a heuristic, and then you will use that heuristic to figure out which path is the best to our goal point. And so you can think of a heuristic as if I was trying to do this cross-country trip from San Francisco to New York. A heuristic is kind of like looking at a map and measuring the distances based off of that, right? Because like if I look at a map and I'm like, oh, from here to here, the shortest distance is obviously like that roughly, right? However, what if here there is a very terrible mountain range, and so going over this takes like 10 days, whereas if I just went like this, it would be shorter. And so the heuristic is like a guideline. It tells us like, this is like an approximation of what it may be, but it can be worse. It can't be better, but it can be worse than what we have. And so we use the given heuristic to figure out which path is the closest to our goal point, and then we follow it. And so the way this is kind of codified, the way we actually do this is very similar to Dijkstra's. The only difference is we add a heuristic to the distance to each node from A. So basically, when I add a node to the queue, I'll do an example right now. So I start with A, and so obviously A is 6 away from E. So the heuristic is telling you how far away approximately you are from E. So we have A and 6, and then we pop it. And then we add both of its children. So we add C, which is going to be 1 plus 4. So that's going to be C5. And B, which is going to be 7 plus 1. 7 plus, which is going to be 8. And again, the heuristic, you can think of it as an approximation of how long the rest of our path is going to be. So we're going to sum up what we already know with what we approximate to be the rest of the path to our goal node. So we're going to pop C. And now we know that this is going to be 2. And this was 3. Got covered by this text, but we're going to have F added. And F has a distance of 1 plus 2 plus 3, so that's 6. And obviously that's higher up on the priority than B, so we're going to pop F. And then we're going to add this item. And so now we have 1 plus 2 plus 1, which is 4, plus 3, which is 7. And obviously that's a shorter path. And so we're going to pop D. And now we're going to add this, which is 1 plus 2 plus 1 plus 1, which is 5, plus 1, which is 6. And so we have B6. I should have just updated the priority up there. B6. And so now we're going to pop B6. And then we're going to say that B6, this is actually 2, so the distance to E is 1 plus 2 plus 1 plus 1 plus 2, which is 7. And then the distance to E from E is 0, so we just pop that like that. And then we realize we've hit our goal point, and we can stop. So the shortest path from A to E is 7, and it goes through here. So A star is a little bit confusing. I completely understand. If you're struggling with it, again, practice problems, always the way to go. But I'm going to move on for now. We're going to go on to the worksheet. And the first problem is just about graph representations. So I'm going to ask you to draw the representation of this graph for matrix form and then for adjacency list form. And I'll give you a couple seconds to think about it. Okay, let's start off with doing the adjacency list form. For the adjacency list, we have A, B, C, D, E, F, and G. So A has nodes, if I go like that, A has nodes B and D coming off of it, like there and there. B has node C coming off of it. So we're going to have, it's just C. C has just node F. D has nodes B, F, and E. So we're going to include B, E, and F. E has node just F coming off of it. And then F has nothing. And G has just F. Now writing this out in the form of maybe I can make this tiny. Great, okay. Now writing this out in the form of an adjacency matrix is going to be A, B, C, D, E, F, G. It's going to get a little bit messy because this is not graph paper. F, G. So obviously A does not have a path from itself, and A does have a path to B. A doesn't have a path to C, does have one to D, and then nothing for the rest. B, on the other hand, only has a path to C. C only has a path to F. D has paths to B, E, and F. So we're going to do that. E has a path to F as well. F has no paths to anything, so we can just zero out that whole row. And then G has a path to F. And so now that's our adjacency matrix version of this. There is also a directed version. This is a directed version. You can also do this for the indirected version. And so for undirected versions, obviously the matrix is always going to be symmetric, because a path from A to B is a path from B to A. So the adjacency list version, if this was a symmetric matrix, will be A, B, C. Sorry, adjacency list version, if this was an undirected graph, would be A pointing to B and D, B having paths to A, C, and D, C having paths to B and F, D having paths to A, B, F, E, and F, E having paths to D and F, F having paths to C, D, E, and G, and then G having just a simple path to F. Because again, if there's any line, doesn't matter which way it's pointing, in an undirected graph, both have A connected to each other. And the adjacency matrix version of this undirected version is going to be A, B, C, D, E, F, G, A, B, C, D, E, F, and G. So obviously A does not have a path to itself. It does have one to B and one to D. B has paths to A, C, and D. C has paths to B and F. D has paths to A, B, E, and F. E has paths to D and F. F has paths to C, D, E, and G. And then lastly, G just has a path to F. And as you can see, if you cut this down the middle, it is a mirror of itself because it is a symmetric matrix. Oh gosh. Go away. Okay. So that's top small. So now we're going to do a quick depth first order search and a breadth first order search of this graph. And so I'll give you guys a second to think about it, and then we will reconvene. Okay, welcome back. So, assuming we're starting it from A depth first search pre-order, if you remember, it means that you visit yourself before you visit your children. So the first thing we're going to write down is just A. Let me add DFS pre-order. So we just write down A, and now we're going to visit its child B, and then we're going to visit its child C, and then we're going to visit the child F. And now F has no children, so we're going to pop back up. C, we're done with all of its children, so we're going to pop back up. And now we're going to see what B has, and again, B has no more children. So we're going to pop all the way back up to A, and we're going to visit its other child, which gives us D. And then from D, we are going to move to C, B, but obviously we've already visited B, so we don't do anything. And now we're going to see if we visit F, but again, we don't need, or I guess we would go with D, E first because it's alphabetical. And of course we haven't visited E yet, so then we will put E. And then obviously we already visited F, so there's nothing to do there. Save news there, and we're done with this whole graph. And G has no paths leading into it, which is why it's kind of alone. So you can just put it in parentheses at the end. Technically, we would eventually move on to the other nodes and start depth first search traversals from them. We will tell you what to do if this ever occurs on a test or anything like that. So for DFS post order, it's just kind of the opposite experience. So in this case, we are at A, but we obviously can't visit it yet because we have to visit its children first. Same with B, same with C. And now I finally get to a node that has no children left that aren't visited. So we add F. And now all of C's children have been visited, so we can visit C. All of B's children have now been visited, so we can visit B. We go back up to A, but not all of A's children have been visited yet. So we're going to take a pop down there, visit C, D, but we aren't going to visit it yet. We're going to go to E instead, and now all of E's children have been visited. So we're going to add E, pop back up, add D, and finally we can add A. And again, G is just kind of on its own. So that's our full depth first search post order. The last thing we're going to do is a breadth first search traversal of this, starting from A. And again, breadth first search is done based off of distance from A, minimum distance from A. So we start off with A itself, because it is obviously 1 away from itself, or 0 away from itself. So we add A, and now we're going to go to B, and then D, because they're both 1 away from A. And now we're going to have C, which is 2 away from A. E, also 2 away from A. And F. And then the last thing is G. It's kind of, again, floating on its own. And now we've seen all of our nodes in a BFS search. So that's our graph representations problem. Now we're going to move on to a Dijkstra's problem. So the idea is, what is the shortest path to every node from A? I will give you guys a second to think about it. Okay, fantastic. So let's start off with drawing our cube. So we have our cube, we have our edges, our nodes, and then we have their weight. Okay, so the first thing we do is we're going to add A, which is obviously 0 away from itself, and then we're going to pop it and add it to kind of our final list. So A, B, C, D, E, F, G. So A is just going to be 0. I'm going to pop this. We're going to add its 2 children, B and D. B has a lower edge weight, so we're going to add that first. And then D has a larger edge weight. And now we're going to visit B, pop that. And the shortest distance is going to be 1. And now we're going to add its child C, which is 3 away. So we're going to pop D, and D now has officially distance 2. And we're going to add its child. Sorry, C isn't 3 away, it's 4 away. I always forget to add. Easy mistake to make. Anyway, and so E's distance is actually 5. Because it's 2 plus 3. And so we're going to pop C, finalize its distance as 4, and add both of its children. So F is going to be 6 away, and G is going to be 8 away. And so we're going to pop E now, which gives us another alternate way to get to G. So let's see if it's better. So that's also 8, so I guess it doesn't really matter. And so now we're going to pop F, and that's going to give us 6. And now we have a different way to get to G that's shorter. So we're going to update G's value with 7. And then that is our final shortest distance from A to every other node in our graph. Moving on. Let's do a similar problem but with A star. And so the goal of this is to find the shortest path from A to G using the heuristic provided. And so like I put the heuristic in little parentheses around, but I mean, it doesn't really matter how you represent it, but yeah, that's a heuristic. So I'll give you guys a second to think about it, and then we will talk about it. Okay, welcome back. So let's get started. So again, we will draw out our priority queue. So we have N, and then we have our weights. So we have A first. So we have A, and A has projected distance 8 from the projected path that goes through A has a weight of 8. So we have that first, and now we're gonna pop it out, and we're gonna add both of its children. So we're going to sum up 1 and 6 to get B, 7, and 2 and 6 to get D, 8. And then now that we've done that, we're going to pop, obviously, the closest item off the list. And now we're going to go to C and add C, which is 1 plus 3 plus 5, which is 9, which is going to go underneath D8. So we're going to pop D8, and we're going to add its child, which is 2 plus 3 plus 3, which is 8. So we're going to move the C down and replace that position with E8. And so we're going to pop E8 out. And for E8, we are going to add its child, which is going to be G 2 plus 3 plus 3, which is, in fact, 8. I meant to write G. So you can pretend that I wrote that above the C. But we're going to pop that, and now we've hit our goal node. So we're going to say, okay, the shortest path is going to be G. Going to be the one that goes like this, and it's going to take time of 8. And so the next question, the really important one, is this heuristic admissible, and why or why not? And the answer is, well, I hope you realize by now that we got the wrong answer, right? Because when we ran Dijkstra, we figured out the shortest path from A to G is actually 7, and it goes up through this whole thing. And so the reason we got the wrong answer is because because our heuristic is not good enough. And so the reason our heuristic is not good enough is, like I mentioned when we were talking in the review slides, you can't have a heuristic that takes longer than the actual path. Heuristic is supposed to be optimistic. Like I said, the map example, when you're looking at a map and you're just measuring out distances, that is the best possible case. That is the case where you are driving in a straight line with no obstacles the whole way through. And so if you look like right here, for instance, we have a heuristic that says there's a distance of 5 left, but 2 plus 1 is only 3. And so this heuristic is not optimistic enough. It's not less than the true path. And so because of that, we didn't go down this path because we thought it'd be too hard, because we thought it'd be always harder than 5. And so we didn't try out the path that would have ultimately been better. And so this is just a quick example of a bad heuristic and what happens if you use it. Okay, well, all in all, that brings us to the end of our worksheet. So I hope you guys have a lovely day. I hope you guys feel good about your midterm. And I'll see you guys next week.